sklearn, linear model, SGDClassifier. A deep dive. The SGDClassifier in scikit-learn implements stochastic gradient descent (SGD) for classification tasks. It's a powerful and versatile algorithm that can handle a wide range of data and be tuned for specific performance needs. Let's break down its features and functionalities in detail. 1. Fundamentals of stochastic gradient descent. Core idea: SGD is an iterative optimization algorithm that updates model parameters by taking small steps in the direction of the negative gradient. Instead of using the entire dataset for each update, it randomly selects a subset of data points, a mini batch. Advantages: efficiency: SGD can be much faster than batch gradient descent, especially for large datasets. Online learning: it can efficiently process data in a stream, making it suitable for dynamic environments. Regularization: it's easily combined with regularization techniques to prevent overfitting. Disadvantages: convergence: SGD might take longer to converge than batch gradient descent due to the noisy updates. Parameter tuning: finding the optimal learning rate and other hyperparameters can be crucial for performance. 2. Key attributes of SGDClassifier. Loss: specifies the loss function to optimize. Common options include hinge for linear support vector machines (SVMs), log for logistic regression, modified Huber, a robust loss function less sensitive to outliers, squared hinge, a squared version of the hinge loss, often used in SVM. Perceptron: the perceptron loss function, simple but less robust. Penalty regularization technique used to prevent overfitting. L2 norm regularization ridge regression. L1 norm regularization lasso regression. Elastic net: a combination of L1 and L2 regularization. None: no regularization. Alpha: the strength of the regularization term. L1 ratio when using elastic net. This determines the mix of L1 and L2 regularization. Fit intercept: whether to fit an intercept term bias to the model. Maxiter: maximum number of iterations for the solver. Tolerance for the stopping criterion convergence. Shuffle: whether to shuffle the data before each epoch iteration through the entire dataset. Random state seed: for the random number generator for reproducible results. Learning rate schedule to use. Constant learning rate. Optimal sets learning rate to 1.0 alpha t1. InviaScaling uses 1.0 alpha t0.5. Adaptive uses an adaptive learning rate. Eta 0 initial learning rate. Powered: the exponent for inverse scaling learning rate 1.0 alpha t powered. Early stopping: whether to use early stopping to prevent overfitting. Validation: fraction of data used for validation during early stopping. Nitenochonge: number of iterations with no improvement before stopping. Class weights for different classes. To address class imbalance. Warm start: whether to reuse previously trained models' weights. Average: whether to average the weights over all epochs. N-jobs: number of jobs for parallel processing. Verbose: controls verbosity of the output. 3. Workflow with SGDClassifier. 1. Initialization: create an instance of SGDClassifier and set the desired hyperparameters. 2. Training: call the fit method on your training data features and target labels. 3. Prediction: use the trained model's predict or predict-proba methods to get class predictions or probabilities on new data. 4. Evaluation: evaluate the model's performance using metrics like accuracy, precision, recall, F1 score, etc. 4. Example code snippet. Python. From sklearn, linear model import SGDClassifier. From sklearn, datasets import load iris. From sklearn, Model selection, import train test split. From sklearn, metrics, import accuracy score. Load the iris dataset. Iris load iris. X iris. Data. Y iris. Target. Split the data into training and testing sets. X train. X test. Y train. Y test. Train test split X. Y. Test size 0.2. Random state 42. Initialize the SGD classifier with desired hyperparameters. CLF SGD classifier loss log. Penalty 2. Alpha 0.01. Random state 42. Train the model on the training data. CLF. Fit X train. Y train. Predict the class labels for the test data. YPREDCLF. Predict X test. Calculate the accuracy of the model. Accuracy score test. YPRED. Print accuracy. Accuracy. 5. Key points to remember. SGD classifier is a very flexible and powerful classifier. But it requires careful hyperparameter tuning. Use cross-validation to select the optimal hyperparameters for your specific dataset. Consider using grid search CV or randomized search CV for efficient hyperparameter search. Be aware of the effects of regularization and learning rate schedules on model performance. 6. YAML configuration hypothetical example. YAML. SGD classifier. Loss hinge loss function used e.g. hinge. Log. Modified Huber. etc. Penalty L2 regularization type e.g. L2. L1. Elastic net. etc. Alpha 0.01 regularization strength. L1 ratio 0.5 mix of L1 and L2 for elastic net. Fit intercept true include intercept term. Maxiter 1000 maximum iterations for solver. Toll 1e-3 tolerance for convergence. Shuffle true shuffle data before each epoch. Random state 42 seed for reproducibility. Learning rate optimal learning rate schedule. Ether 0.01 initial learning rate. Powered 0.5 exponent for inverse scaling. Early stopping true enable early stopping. Validation fraction 0.2 validation data fraction. Nitenoshonj 5 iterations without improvement before stopping. Class weight balanced weights for different classes e.g. balanced. Warm start false reuse previously trained model. Average false average weights across epochs. N jobs -1 use all available cause. Verbose 0 verbosity level. This YAML snippet demonstrates how you can define a configuration for your SGD classifier. The keys represent the various hyperparameters of the algorithm. And the values are their corresponding settings. It's crucial to carefully choose these values based on the specific problem and dataset at hand. This comprehensive overview provides a solid foundation for understanding and utilizing the SGD classifier in your machine learning projects. With careful tuning and experimentation, it can become a powerful tool for achieving impressive classification results.